But now let us move on to the radial part. The radial part of the equation is looking like this. That also has L square. Why does it have L square? Of course, because you equated the radial part and azimuthal part to the same constant. So, that has L square in it. This is a second order differential equation now, and now you have to worry about core and cladding, because it is still n r square. So, you have to, you do not know whether you are writing it for the core or for you should. So, should you write it for the core or should you write it for the cladding? Core. But the wave should get supported in the cladding also, in the sense that it is not a metallic waveguide. It is not a metallic waveguide where the wave is kind of attenuated to 0 at the boundary. Metallic waveguide will demand that the boundary condition says that the electric field at the boundary should reduce to 0. That does not happen here. It is a dielectric waveguide. So, the difference is that the electric field has to actually continue and it has to attenuate in the cladding. So, should I write it in core or should I write it in cladding? I should write it for both. I should write it for both core and cladding, and I have to apply the boundary condition and figure out a solution which is surviving in core and decaying in cladding. Okay. So, I have to first write it in core. So, how do I write it in core? That is easy. N square r should be replaced by N1 square, and for cladding N2 square. So, for core I rewrite the same equation with N1 square, for cladding I rewrite the same equation with N2 square. Okay. Now, there are two possibilities here. Okay. One possibility is where your beta square. So, whether the solution is oscillatory or decaying is decided by the magnitude of this k naught square n square minus beta square. If this number is positive, k naught square minus n1 square minus beta square, if that number is, without really deriving this, I am telling you that if this number is positive, then the result is a nice oscillatory solution. But if this number is negative, so you can immediately say that this beta square must be less than k naught square minus n1 square, but at the same time it should be greater than k naught square minus n2 square. So that here it becomes decaying and here it becomes oscillatory, or you get a surviving solution here. So, if your k naught square beta square is less than this and beta square is greater than this, the same condition I have told, in that case the solutions are oscillatory in the core and they decay in the cladding. It all depends on the sign here. If this sign turns out to be negative, it is decaying solution. So, you are now putting a condition for deriving modes of the fiber. In other words, you are saying that if it has to be a mode in the fiber, if it has to survive in the core and if it has to decay in the cladding, we demand that beta square must be of this nature. It also says that, you know, beta square assumes only because the solution gives some specific beta square. So, these beta square assumes only specific discrete values, and that defines the guided modes. Why do you call guided modes? Because we put in this condition that it is available only in the core and not available in the cladding. Now, you see, for a given value of L, you could have certain number of values of beta square that are possible. For a given value of L, which came from your azimuthal, you know, that equation constant, for a given value of L, what are the allowed values of L? 0, plus minus 1, plus minus 2, and we said plus minus 1 and plus minus 2 is giving you the same field. So, it will give you, it is just 0, 1, 2, 3. For each 0, 1, 2, 3, if you solve this equation is going to give you m values of beta. Okay, for each value of L, it can give you m values of beta. So, totally how many values of modes will you get? How many allowed modes will you get? For each value of L, you get m values of beta. So, you will get L times m number of modes supported multiplied by 2 for polarizations. These are the number of modes supported in the fiber. Okay. So, for L equal to 0, I could have one value. L equal to 0, I could have m is equal to 5 values, I could have 10 values, I could have 20 values, depending on what my n1 square is and depending on my dimension of the fiber. Then for L is equal to 1, I could again have 3 values, 5 values, 10 values, depending on how this equation, how I am getting the solution. So, in total I could have L times m times 2 times number of modes supported in the system. So, the question is, will I get different values for each of these modes? Yes, I will get different beta values for each of these modes. The question is a degeneracy with respect to phi only, or is it with respect to r also, r and phi also? So, what happens is, for example, if I have LP, so this gives rise to LP-LM. This is how we designate the mode number, LP-LM modes. LP01 mode, for instance, tells you that L equal to 0 and m is equal to 1. What is the degeneracy of this? L equal to 0, irrespective of what my m is, it has only phi degeneracy of 1 and it has 2 polarization degeneracies. So, how many LP01s or how many degenerate LP01s can I support? I can have a LP01 with a specific, so a specific m means a specific beta. Okay. So, LP01 with X polarization, I can have an LP01 with Y polarization. So, I can have only 2 degenerate modes which I can call as LP01. Okay. But suppose I take a mode which is, let us say, LP02, okay, or LP, let us not take LP02, LP11 for instance. So, I have L is equal to 1 and m is also equal to 1. Now, m is equal to 1 means a specific beta is already assigned, okay, but L equal to 1 could mean a cos phi solution or a sin phi solution. So, a specific assigned value of beta can give a cos phi solution or a sin phi solution, and it could give an X polarized solution or a Y polarized support. So, how many degenerate modes are possible here? 4. So, you have answered the question. Okay. So, when you have m values of beta, it actually m distinct values of beta. You get m different values of beta when you solve the radial equation. Okay. So, then the question now is, it is very important to solve the radial equation to find out what these betas are, right. Not just that, the radial equation not only helps you to find beta, it also helps you to find r. You are actually finding out r also from here, and once I know r and I already know my phi, I can construct my entire solution. So, the other possibility we said is, what happens if this becomes positive, in the sense that when beta square is less than k naught square and 2 square. What happens in that case? In this case we demanded that this became negative, but in this case this is not becoming negative, it is still positive. It means that I have oscillatory solutions in the cladding also. I have supported modes in the cladding also. Okay. Now, these solutions are oscillatory in core as well as cladding. Of course, they were oscillatory in core because that is decided by your this n1 square condition, but they are oscillatory in cladding also, which means these are supported where? These are supported in the entire fiber, core, cladding, everywhere, right. The point is, it turns out that beta square will now assume, you won't get discrete solutions if I have both these conditions satisfied. You can have beta square as a continuum of values because there are no restrictions you are placing. You are not putting any kind of restrictions here. So, beta square can take any value. So, what these modes are called? They are called radiation modes or cladding modes. Do you wish to have cladding modes or you do not wish to have cladding modes in a fiber? In a fiber which is used for communication. Do you want to put your energy in cladding? Then you should have cladding modes. then you should have your beta square corresponding to less than k naught square into square. So, you really do not wish to do that. So, typically we try to make sure that the beta square or let us put it this way, for all the guided modes this condition is satisfied. Now, I can connect it to the in the beginning of the lecture we said that these modes correspond to different angles. Okay. What are those angles? Allowed angles even after satisfying the critical angle condition, right. So, I can say that each of these LP-LM can now correspond to different angles. What about the angle for a radiation mode, for the cladding mode? It is less than critical angle, it is escaping into the cladding, it is primarily residing in the cladding. So, there is no restriction for beta because there is no interference condition to be satisfied in the core, right. Remember the origin of modes, how did we understand? We said that there are multiple reflections, and between two successive reflections the wavefront should maintain, if it is a plane wavefront it should maintain the same phase, and we put some conditions there. But if the energy is available in cladding, there are no such conditions to be put, which is why your beta can assume a continuum of values. So, in short, if I put some energy into the fiber, in general, if I do not do launching at a specific angle, or if I just expose the fiber to energy incoming in all directions, what can I say in general? I can say that my energy gets distributed between guided modes and the radiation modes. So, in general, any arbitrary field distribution you can expand, arbitrary field distribution at the input, okay. You can expand it as sum of guided modes. Each of these modes will have a certain Lm, corresponding to the Lm there is an R phi, and there is a strength, corresponding strength, how much power do I excite in each modes, and these are your radiation modes. So, this is your guided modes and these are your radiation modes. In general, if I do not do anything special, I am distributing my energy between the guided modes and the radiation modes. If I were to use a fiber for communication where I want to confine all my energy in the core, what should be my attempt? My attempt should be to adjust my launching condition such that all the energy is in the guided mode and I do not have any radiation mode. Suppose I have a source which is doing this, I will keep the fiber here and try to get light outside. What actually happens in this case? The light is propagating in all possible angles, and so it gets launched in all possible angles, and then what happens? It will get distributed between the cladding modes and the guided modes. So, instead if you put a lens, I should draw a big lens here, put a lens and try to focus the light into the fiber such that my focusing angle now matches with the numerical aperture acceptance angle of the fiber, then I can assure that all my energy is in the guided mode. Okay. So, that is a fiber launch condition. Now, you can check what is the numerical aperture of the lens that you are going to use, what is the numerical aperture of the fiber that you have, are they matching, and are you trying to couple efficiently and so on. Okay. So, we have not still solved the wave equation, we just now talk about guided modes and radiation modes. What does it require for you to solve now? I have to do a brute force solution for that second order differential equation. So, this is my second order differential equation. Of course, it is in the core and the cladding it is different. Okay. Now, there are too many variables here. So, we are going to change the variables. We are going to change the variables to this one we are going to call as u square multiplied by the core radius, I mean, or rather this divided by u by a is what I am calling. So, I am calling this as u divided by a the whole square, this one, and this one I am calling as w divided by a the whole square. U is a constant or a variable? Do I know u or do I do not know u because beta is unknown. So, u is unknown, w is unknown. Okay. In fact, from one unknown I have actually moved to two unknowns now, but I am doing this because one is for the core and the other one is for the cladding. The benefit of doing this is that if I do u square plus w square, what do I get? Minus beta square and plus beta square will get cancelled. U square plus w square is something that I know. Okay. So, u square plus w square is what is called as the V number, V of the fiber, and that is a times square root of k naught square n1 square minus k naught square n2 square. This is going to prove to be a very useful number for a fiber. Okay. It gets defined this in a very indiscrete way, but then remember this number is going to be very useful. Okay. Now, do I know V or do not I know V? I know the value of V very well, that is defined for a fiber. Once I pick a fiber, V is defined for the fiber. So, V is one characteristic parameter of the fiber, and that is called as the normalized waveguide parameter, or it is just simply called as the V number of the fiber. So, if you look at fibers, you will say V number, and V number can decide the modes of the fiber, and we will see how V number decides the mode of the fiber. So, in the core you rewrite as u square r square by a square. In the cladding you will rewrite it as, you see I defined cladding as beta square. Why did I do that? So that you get a negative sign here, because we wanted the solution in cladding to be decaying. Okay. So, we stop at this point and we look at the solutions of these equations. Now, I do not know how many of you have done a differential equation course.